In this new playlist, I will be talking about expectation maximization for NLP tasks. So I want to know how we can use or write NLP tasks in a different framework, how we can use latent variable models and graphical models in order to reformulate the problem of NLP tasks so that we can create more scalable, hopefully more interpretable algorithms for natural language processing tasks, such as summarization or question generation, question answering, story generation, and so on. So one example is latent part of speech, latent POS sequences for neural machine translation. As you know, neural machine translation, we want to improve these models. That's why even today we are working on machine translation very much, because we can use, for example, here we can use latent part of speech sequences. Someone else could use other techniques such as dependency parsing, discourse parsing. And there are many ways to improve neural machine translation. So let's focus on how we can think about part of speech sequences as a latent variable Z. So learning target site syntactic structure has been shown to improve neural machine translation. However, incorporating syntax through latent variables introduces additional complexity in inference, as the model needs to marginalize over the latent syntactic structure, because it's a sum. So for sum over Z, so at each time you should marginalize, so it takes a lot of time, and you will see what kind of tricks I will introduce so that you can get rid of that or even reduce the computational complexity that arises from this marginalization. So Latent infers the syntactic information at a given position based on the source text and the partial translation context. For example, in previous methods like this one or this one, as you see, Z is dependent on Y, the history of Y, and so it's very messy. But here it has more simplified structure. Z is not dependent on yn-1, for example. And so this one is the algorithm that I will explain in this lecture. So because we have this latent variable, the model cannot be trained because it becomes non-convex if you want to directly optimize the data likelihood. So figure 1, this one is an ideal solution that captures full codependence between syntax and semantics. Semantics is the output, Y, because Y is a translation token, and Z is the syntax because it's part of speech. For example, it could be verb, subject, object, and so on. So Z is syntax. It could be part of speech, but Y is the output. the output as a meaning, it's translation of that. So it has semantic meaning in the word space. And finally, this is the model that we want to concentrate, this model. You see that Z affects Y, but at the next stages, Z is dependent on the history of Y and not dependent on previous Z. For example, Zn plus 1 is not dependent directly on Zn. And why we do this? Because we want to get rid of computational complexity at inference time. For example, Zn is not dependent on Zn minus 1 directly. It is dependent on that indirectly through another variable, which is your output at time n minus 1. So this is the marginalization, because if you're summing over Z, so Z is syntactic information because it's part of speech tokens. And the main difficulty, however, is that inference in this model is intractable, since it involves marginalizing over latent Z sequences. So that's why we want to use new expectation maximization. And so this EM is very, very popular in computational statistics. And for example, many latent variable models, we use expectation maximization. And it is, some people argue that it is not scalable, but I say that it is scalable if you use it properly. For example, I will explain it later, or even in other lectures, how we can use it effectively. So this is the idea. You are sampling Zn through this. So this is the expectation, because at the expectation step of EM, you use latent variable models. But for the maximization step, use the output, I mean translation. Here is translation. And in another problem, it could be another thing. So this is a back and forth between two models, expectation and maximization. So first you give the input. Your input could be a set of words in a sentence. And then through an inter-retention, and also you get the history. You need to know the history, for example, translation up till time step n. And then now the expectation step starts. And you sample Zn. Now once you have sampled Zn is fixed. So now here Zn is fixed. That's why it is tractable to calculate the probability of your output, which is the translation at time step n. And so, as I said, Y and Z and the probability, because they are independent, now Yn and Zn, because the probability of Zn times the probability of Yn dependent on Zn. And here we are talking about inference with exhaustive search for latent states. So when using traditional variables to model target site syntax, exact inference requires marginalizing over these additional variables, Z. So to avoid this exponential complexity, prior works use a two-step decoding process with models similar to the one shown in figure 1b, this one. They use greedy or beam search to explore a subset of the latent space to compute the posterior distribution as follows. So they use this marginalization. So finding the most likely translation, because now the output is y is translation, using this model requires marginalizing over latent states. However, because the latent states don't directly depend on each other, as I said, we don't have these connections in this model. We don't have these connections. We can exhaustively search over the latent states. So we don't have the problem of computational complexity. So when y is fixed, I mean the previous one, that y is fixed. For example, here y is fixed, translation up to time n. Then when y is fixed, it is, partially observed, translation up to time n. The Zn, which is the latent variables, are de-separated. If you look at the beautiful book of Bishop in 2006, he works in Microsoft, they are mutually, we call they are mutually independent. The same meaning. As a result, the time complexity drops significantly from this to this. And this reduction of complexity is the essence of this article, is the necessity of writing this article. And so the posterior distribution for the translation probability at a time step n can be computed as follows. So you have x, x1, x2, xm. For example, in GRU or LSD, these recurrent neural networks, we pass it in to get the hidden variables are passed. And finally, if you go to the decoder step, which is, for example, y1, y2, y1, y2. The output, y1, y2, y3. So these y's are translation, and what you're giving is a sentence. You're giving sentence, and you get the out. So y1, if you know y1, it comes to your y1. y2, you sample, it becomes y2. Now you fix it, you give it to this, and so on. So that's why we are generating a sequence. So now we can do the training with neural expectation maximization. So directly optimizing the log likelihood function, this equation, with respect to model parameter theta is challenging because of the highly non-convex function P of y and z n. This one is non-convex. Alternatively, we optimize the system parameters by expectation maximization. And we need a trick, just like we did a trick lower bound for that variational autoencoder. So here we use Jensen. Why do we use Jensen inequalities? Whenever we have a convex function, we can use function. Something is convex, log of it is also convex, and so on. So we can use this trick, this inequality, to get a lower bound. Because once we maximize the lower bound, it's just minimize the main objective. So we are reducing this gap, as I've explained several problems. And finally, we apply this expectation maximization. So in expectation step, we just calculate the probability of latent variable. This is the way we do in EM algorithm. Once we have calculated, we fix it and we go through maximization step, which is just the update theta using this gradient this gradient of the objective. But now objective is just the lower bound. So this is the step for maximization. And by the way, we want to use regularization, so we add another term in order to do a regularized version of expectation maximization. So in E step, we just calculate the Zn probability. And then after we sample it and fix it, we can do maximization, because we are now learning the parameters. In E step, we are evaluating the latent variable, but in M step, we are just learning the parameters. So parameter theta is different from latent variable Z. In expectation step, we evaluate Z, but in the maximization step, we are trying to learn Z. Because we have now fixed Z, now we are learning theta in maximization step. Oh, sorry for breaking the silence. Zn is the part of speech. For example, a sequence of Z1, Z2, Z3. For example, here is verb, here is subject, here is verb. So it's the part of speech sequence that is coming when we have this sequence, this sentence.